So welcome to our first video as a review of Chemistry 1 as an introduction to Chemistry 2. Today's video, we're just going to get into the very basic chemistry stuff. I usually just like to review this because it's always good to know what atoms and molecules are, and of course, it's good to know how to calculate significant figures. If you had me before, you will know that I'm a stickler for those sig figs. So we're going to cover those in this particular video as well. So I'm going to kind of go through this quickly because there's just a lot of very basic concepts. Hence the name of this video, Getting Back to the Basics. So let's go ahead and do that. So a couple of different types of matter. Of course, we have atoms. That's what makes up everything in the periodic table. Atoms are the smallest unit of an element that maintains the properties of that element. So I'm going to read these to you, and I'm going to go through these notes. What I ask you to do is to take notes in that note packet that I sent to you as well. And what's nice about doing these is that you can pause this video and write these down. So that way I can actually go through this a little bit faster. So by all means, pause this if you need to at any point, write whatever down that you need to write down, take notes of things that I'm saying as well. Anyway, so atoms, the smallest unit of an element that maintains the properties of that element. So you can't break atoms down any more than what they already are. If you do, those atoms are no longer that particular element. For example, you might remember in Chem 1, we talked about the number of protons in the nucleus. It determines an element's identity. So if I were to break apart a helium atom, which has 2 protons in its nucleus, because it's number 2, on the periodic table, it's no longer going to be helium. So the smallest unit of an element that maintains the properties of that element. It has to have a certain number of protons in order for it to have specific properties. And all of the elements that we know of on the periodic table, there's 118 right now. Those are the smallest unit of that element that we can get. And we're going to get into later in the year nuclear chemistry, actually, which is what happens when atoms, especially those heavy metals, are not that stable. Of course, we can take these atoms and combine them together. So when you take atoms and combine them via chemical bonds, you produce molecules. And molecules can sometimes be broken down. We're going to get into the nitty-gritty of molecules versus compounds here in a second. But a molecule is when any atom joins another atom by producing a chemical bond. So it doesn't have to be the same atom. They don't have to be different. They're just any 2 atoms that have to be bonded to one another. For example, if I have hydrogen bonded to itself, that is going to be an example of a molecule. It's 2 atoms that are bonded. Compounds are similar to molecules, except a compound is a very specific type of molecule. So compounds have to be when 2 or more different atoms join. So that's the key difference between molecules and compounds. Molecules are any 2 atoms that bond, whereas molecules have to be different atoms that bond. And as a result, because we have different atoms that bond, you can break compounds down into something more simple and more stable. And a perfect example of a compound is water, so H2O right here. So of course, water is comprised of hydrogen and oxygen. You have different elements there. Hydrogen is bonded to oxygen to make the water. Because you have different elements that comprise that molecule, you can break that molecule down into its elements. And typically that's done by something known as electrolysis. I'm actually going to cut out here and show you an example of that in just a second. But compounds can always be broken down, whereas molecules cannot always be broken down. Sometimes they can, sometimes they can't. And this is that prime example of like all compounds are molecules, but not all molecules are compounds. Like everything or all rectangles are squares, but not all squares are rectangles. Like it's that kind of thing. So everything that's considered a compound is a molecule, but not everything that's a molecule is considered a compound. I'm going to cut out here and I'm going to show you an example of this on the whiteboard on my screen. So I wanted to show you the difference between molecules and compounds. So again, molecules are any two atoms that are bonded. So a good example of a molecule is bromine bonded to itself. So I have Br2. Bromine is considered a molecule, of course, because it's bromine bonded to another bromine. So I have bromine bonded to bromine there, but I can't break bromine down into something more simple and stable. This is already one type of element, so this can't be broken down. Again, it's already simple, it's just bromine. On the other hand, if I have something like water, where water is, of course, hydrogen bonded to oxygen, you can break water up so it's more simple and more stable. And you can break water up into its elements, into hydrogen and oxygen. And they have those subscripts of 2 after there for reasons we'll get into later as we progress through this review. But this can, in fact, be broken down. And that's because water is a compound. And it's a compound because it's more than one type of element that's bonded together. Typically, you can break compounds down. The most common way to break water down is by something known as electrolysis, which is when you run an electric current through something. You can also break compounds down by heat, sometimes, not all the time. More complex compounds, you can typically do that. Water is also considered a molecule, however, and that's because it does follow that basic definition of a molecule. It is 2 atoms bonded. So water is a molecule and it's also a compound, whereas bromine does have 2 atoms bonded, so this is a molecule, but this is not a compound, and that's because it does not have different atoms that are bonded. Notice how molecules don't have to be the same atom that's bonded. This water is categorized as both a compound and a molecule. Like I said, it's kind of like that thing where all squares are rectangles, but not all rectangles are squares. I'm sure you can think of a lot of examples with like sayings like that. But molecules do not have to be the same. They're any 2 atoms, whereas compounds have to be different, and that's because you can break compounds down by either electrolysis or you can break it down by heat. So let's get into the states of matter. We have solids, we have liquids, and we have gases. Of course, you've learned a lot about these in Chem 1. I'm sure you've also learned about these even in middle school. Well, we're just going to review them again just so everybody is all on the same page. The way I teach Chem 1 is I like students to know the types of energy that each of these different states of matter has. So solids have only vibrational energy. So they vibrate back and forth like this. And because they only vibrate, they can't slide past one another. And because they don't slide past one another, they keep their shape. They have a defined shape. So if I take a look at, I just have this lipstick right here, so I'll show you this. But all of the particles that make this up are in the solid state of matter. And even though it doesn't appear that those atoms are moving at all, They are, in fact, vibrating back and forth. Even when you, as a person, have absolutely no energy, you are moving a little bit, and atoms are the same way. They're vibrating back and forth in place. Because they're just vibrating, it's going to keep its shape because they can't slide past each other. When you've reached a point called absolute zero, that's actually when particles stop moving completely. But everything that is a solid is in fact vibrating back and forth. And that's true for any solid. This pair of scissors that I have right here, I have a mouse, right? So all of these solid particles are vibrating back and forth, which is why they keep their shape. They're also not compressible. I can't take something and make it take up even less space because the particles are already packed very tightly against one another. And their volume is also defined. Here's a drawing. So particles are very, very tightly packed within a solid. Notice that they keep their shape, and that's because the particles are simply vibrating back and forth. They can't take the shape of the container that they're in because they don't have enough energy to do that. They can't slide past one another. Liquids, on the other hand, can slide past one another, which is why they take the shape of the container that they're in. So if you have a bottle of water sitting in front of you, you could shake that water around and it takes the shape of its container. You pour it in a different container, it takes the shape of that container. Why? That's because liquids, they don't only have vibrational energy, not only do they vibrate back and forth, but they also translate. And translational energy means they could slide past each other. So they can take the shape of the container that they're in. So as a result, its shape is undefined. Water molecules, excuse me, gotta get by, right? So they could slide past each other in a container, hence why it takes the shape of whatever container it's in. Liquids, however, are still not compressible. You can't take a liquid and make it take up less space, and that's because the particles, similar to solids, are also still very tightly packed with one another. So their volume is also defined. I can't make a gallon of milk become a quart of milk. And that's because the particles are already packed very tightly against one another. Notice in a liquid, you can't see the space in between the particles. The space between them is still very, very, very small. But they do take the shape of whatever container they're in because they have that added translational energy. Gases, on the other hand, not only have translational energy, not only do they have vibrational energy, but gases have another added type of energy, which we call rotational energy. And that rotational energy is what allows for gases to take up massive volumes. That's why the air in the room that you're sitting in is taking up a lot of space, is because they have that added rotational motion, and the particles are very, very, very far apart relative to their size, which that's something we'll talk more about when we get into the gas law unit, actually. Gases also have an undefined shape. They can take the shape of whatever container that they're in. It doesn't matter. However, because gases have a lot of energy, if you just look at this, gases have 3 different types of energy as opposed to solids have just 1. If I give the class 10 Red Bulls each, you're not going to want to sit in a very small space. You're going to want to be very far apart from one another, probably on the football field, running around like crazy. And gases are the same exact way. Because gases have a lot of energy, those particles are very far apart from one another. You can take those particles that are very far apart and compress them. So gases have a very high compressibility. I can take a gas that takes up a volume of whatever this is and have those particles take up half the space. And that's because I can force those gas particles closer to one another. a result, gases also have an undefined volume. So you could take, like I just said, a gas and make it take up less space. And that's because there are a lot of space in between the particles relative to their size. So just look, you can literally see space in between these particles. As a result, you can force those gas particles to get closer to one another. And that, of course, when we do that, we're increasing pressure, which is something we talk about in one of our first units, the second unit, actually. It's all about gas laws, and we talk about pressure there. So that's the major difference between those three states of matter. And of course, in order to go from one state of matter to another, we have to increase or decrease the amount of energy those particles have, and normally that's done through heat or temperature. So when you increase the temperature, typically something will go from a solid to a liquid. You're adding energy to that system. Whereas if you take energy away from a liquid, the energy that's going to go away is your translational energy, which turns it into a solid. And we can classify changes of state by looking at each of these. And I know you're very familiar with these, so I'm just going to go through them quick. Solid to a liquid, of course, is melting, whereas a liquid to a solid is freezing. Even though something is not cold, it does not mean it is not frozen. So this mug right here is considered frozen because it is in its solid state of matter. Liquid to a gas is vaporization. Notice it is not evaporation. Evaporation is typically associated with water only, whereas vaporization is any liquid. Gas to a liquid is condensation. You see that if you take a hot shower on a cold morning or a cold night, those water vapor molecules from the hot shower, they'll condense on the cold window and become a liquid. Two you might not be so familiar with. A gas to a solid is called deposition. You see this a lot of times in the winter if you park your car outside. So you're running late to school and you go outside and you say, oh my goodness, I have all of this ice on my windshield. That ice, even though there was no storm last night, there was no snow, why is there ice on the windshield? That's because the water vapor from the air hits your super cold windshield and becomes a solid right away. It actually skips the liquid phase entirely. That's why you'll come outside and you have those really intricate crystals on your car windshield, which is a pain in the neck to scrape off. If you go from a solid to a gas, that is known as sublimation, skips the liquid phase entirely. You see that a lot of times with dry ice, which is solid carbon dioxide. So let's talk about significant figures, one of my favorite things. You have to become good at this. And we use significant figures all the time. So open up those Chem 1 notes, dust those off, and become familiar with these significant figures again. So let's go over the rules. Any number that's not a zero is considered significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9, those numbers are always significant. For example, the number 87 has two significant figures. When a zero is surrounded by non-zero numbers, it is significant. When a zero is trapped or sandwiched, what I usually say. And if multiple zeros are trapped or sandwiched, all of those zeros are significant. So for example, the number 209, 209 has three significant figures. That zero counts there because it is trapped or sandwiched. When a decimal is in the number, the first non-zero number present and all the numbers after it are significant. For example, if I have the number 9.70, my first number that's not a zero, which is the 9, is considered significant. And therefore, because there's a decimal, everything after that 9 is significant. So this value has 1, 2, 3 significant figures. As opposed to this number has only one significant figure. And that's because your first number that's a non-zero is the 4. That number is significant, but because there's nothing after it, There are no other significant figures. Therefore, these zeros in the front act as placeholders. They act as placeholders. Technically, you can rewrite this in scientific notation, which is why this value has one significant figure. And the last rule, when a number is written in scientific notation, all of the numbers to the left of the multiplication sign are significant. So a number you hopefully remember, 6.023 times 10 to the 23rd, Avogadro's number, you have 4 digits to the left of the multiplication sign, and therefore all 4 of those digits are considered significant. So let's just go ahead and do some examples together.
So sample problem 1. I don't know if right now the sound on this is going to be any different. I am filming this at school just to give this a shot. So I guess I'll see how the quality is when I get home, but I'm using the microphone of the Ziggy, and I have my little tablet here to draw on at school as well. Anyway, let's go ahead and count the number of significant figures in each of these numbers. So for letter A, and really all of these, any number that is not a 0 is considered significant. So if I have this 2 and this 5, both of those are considered significant because they are not zeros. However, because I have a decimal in this number, which is right here, and I have numbers that are not 0 in front of that, that 0 is also considered significant. So this particular measurement will have 3 significant figures. And again, we always use significant figures with measurements, and that's because there's some uncertainty in our measurements. When you put a sample of something on the scale and the scale reads to you 1.92 grams, that particular item is not going to be exactly 1.92 grams. It's approximate. We don't know these digits that come after the 1.92. This could be 0.755 blah, 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 grams after that. So therefore, we have to consider that when we are doing calculations, which we're going to do after this. B, on the other hand, also has those 2 digits that are not 0, but it has no zeros at the end of it. So this particular digit will have 2 significant figures. Notice the difference between A and B. A is a little bit more precise of a number than B is. Little bit more certainty here, 25.0 versus 25. Let's take a look at C. So whenever I have a problem like this, I always put my pen down if there is a 0 in the front of a value, and I just cross out all those zeros in the front. And that's because those zeros are considered insignificant. There's no other number that's not a 0 in front of them. And therefore, any number that's left over is considered significant. So this number has 1 sig fig. And the reason for that is because technically you could take this number and rewrite this in scientific notation. And when you do that, you actually obtain 1 significant figure as well. There is 1 number to the left of the multiplication sign, just like that 4th rule up above states. D, I also have a 0 in the front. So once I see that 0, I'm going to put my pen down and I'm going to cross out all the zeros until I get to the first one that's not a 0. And when I do that, I get to this 2. So I only cross out that first 0 there. And in this case, every number after that is also considered significant. So this value will have 4 significant figures. I love this next example, and if you've had me before, you've heard me talk about this. So I love the show, My 600-Pound Life. And when you watch that show, not everybody on the show is exactly 600 pounds. They are approximately 600 pounds. They're about 600 pounds. Therefore, that value, that measurement in that television show, my 600-pound life, has one significant figure. And that's because that's an estimation. It's about 600 pounds. That's how much approximately everybody weighs. If the show instead was called My 600 Pounds Life, I now have a decimal point in this number, which makes these 2-second zeros significant. Therefore, this number is quite a bit more exact. This one has 3 significant figures that makes up that particular value. If the show was called My 600 with this many zeros, Pound Life, probably a lot more difficult to get those people that weigh exactly that mass to go on the show. Why is that? Well, because first of all, our weights fluctuate every day. So somebody who's on it today is not going to be on it tomorrow. But there's probably no person that weighs exactly 600 pounds with 1, 2, 3, 4, 5, 6, 7, 8 significant figures as this particular value has. So because we're dealing with measurements, we have to consider how exact are these numbers really? How accurate are they? What's the uncertainty in each of those measurements? And again, all of these are for measurements. So if we didn't get that down yet, let's go ahead and get that down. We use significant figures all the time for measurements. F. So again, I have a decimal point in the beginning. I'm going to put my pen down, cross out all those zeros in the front, and notice I have 3 significant figures here. Here I do have a decimal. So because my first number is a 5, all of these numbers are considered significant. They are important to that value. Same thing for H. I have a decimal point in this number. My first number that's not a 0 is the 3. Therefore, all of those numbers are significant. Therefore, there are 6. The second number has only 2. This is approximate, about 150. So if you have $150 in your bank account, you tell a friend, oh yeah, that's how much I have. You might not have exactly $150 in your bank account, but maybe you have 149.56. So 150 is not the same as 149.56, but you're rounding, you're estimating. It's just, it's a little bit uncertain. It's not exact. J has 4 significant figures. Let's go ahead and do these 2. So K has 1, 2, 3. There is a decimal. 4, 5, 6. All of those count. And L. L is one where we utilize that last rule. Everything to the left of the multiplication sign is significant. So for letter L, this value has 2 significant figures. I want you right now to do M through T. Pause this video and check your answers with me. I'm going to have the answers back up here as soon as you restart the video. And there's your answers for the rest of those there. If you want some additional practice with counting with significant figures, you're more than welcome to complete part of the worksheets that I gave to you, or you can always look online. Just Google practice with counting significant figures worksheet or videos even, and you'll see so many resources that will help you out with this if you need it. Let's go ahead and get back to the notes.
And then, of course, chemists don't just sit around and count the number of significant figures in numbers, but they do calculations with these measurements, really. Significant figures are useful for measurements, not just numbers, which is why you've never talked about them in a math class before, is because math class typically doesn't use measurements. But chemists, we measure graduated cylinders, rulers, thermometers, lots of different things. If you are adding or subtracting while using significant figures, your answer will have the same number of digits to the right of the decimal point as the number with the fewest digits to the right of the decimal point in the calculation. You have to look at how many digits after the decimal point do each of the numbers you are adding and subtracting together have. I think it's easier to actually do this on paper than it is to talk about how to add and subtract. So I think when we go over the calculations part together, it'll make a little bit more sense. Whereas multiplication and division is a different rule. So your answer will have the same number of significant figures as the number with the fewest number of significant figures used in the calculation. So you're not looking at decimal points here. You're looking at how many significant figures does each number have, and your answer has to have the lower number of significant figures. Very, very wordy. So let's just go ahead and do sample problem 2 together. This should hopefully refresh your memory.
Calculate each of the following to the correct number of significant figures. So using those two rules, we can determine how many significant figures will be in our answer, because again, we can't be more exact than our least exact measurement that was used in that calculation. The easiest part about all of these is first just doing the math like you would in any of your math classes. So when you type in for letter A, 651 times 75, your calculator tells you an answer of 48,825. That is way too exact if both of those numbers that we were multiplying together are measurements. So we have to consider how many significant figures are in each of those measurements in the beginning. 651 will have 3 significant figures, whereas 75 has 2. When you're multiplying, you have to consider how many significant figures are in the least precise value, and that's how many significant figures should be in my answer. So we have to round 48,825 until it has 2 significant figures. Therefore, you would round this number up to 49,000. 49,000. A lot of times students will say, okay, well, I know I have to cut it off here. That 8 rounds that 8 up. And then they'll say, okay, it's just 49. 49 and 48,000 are very different numbers. So make sure you tack on those insignificant zeros at the end. B is the same thing. We're dividing and it's the same rule. So first things first, I'm just going to plug that into my calculator as it is to get an answer. And I happen to get 3.134. This first value has 4 significant figures and the second one has 2. So I have to round my answer so it has 2 significant figures. Therefore, I'm going to chop my answer off in between this 1 and this second 3, and my answer expressed to the correct number of significant figures would be 3.1. C, again, just typing it in the calculator, 500 plus 432 plus another 2 gives me 934. It's much easier, I think, to just write the real answer down first, especially when you're just doing significant figure calculations. We have a different operation here, and therefore it's a different rule. So we are adding. Adding and subtracting uses the same rule, and multiplication and division uses the same rule. In this case, we have to look at the value in each of these numbers that I added together, which one has the least number of places after the decimal point. Well, 500 has 0 places after the decimal point, right? You could see there's nothing there. 432 also has 0 places after the decimal point, and so does 2. Therefore, your answer should also have 0 places after the decimal point. And in this case, the calculator gives you the correct answer. This is expressed to the correct number of significant figures. So sometimes the calculator will be accurate. However, believe it or not, You are smarter than the calculator, so you have to sometimes round your answer appropriately. The calculator is not assuming that these numbers you're typing in are measurements. We'll do D and E. So 360 times 51 times 9.07. Calculator gives me this ridiculous number, 166,525.2. I'm multiplying, so I do have to consider how many total significant figures are in each of these numbers. 360 has 2. That 0 is insignificant because there's no decimal at the end. 51 has 2, and 9.07 has 3. Therefore, we have to round our answer so it has 2 significant figures, the lowest amount. Now, this is going to be a pretty big round because right now this value is 166,525. I'm going to chop this number off right here. So I know everything after these first 2 digits has to be an insignificant 0. That 6, however, will round that first 6 up to a 7. So your final answer would be 170,000. E, little pain in the neck, E is, but it's not impossible. It's just got a lot of decimals in there. Just type those in your calculator first. And the answer your calculator tells you is 24.614829. We need to round this appropriately using the rule for addition and subtraction. And for addition, we have to consider which one of these numbers has the least number of places after the decimal point. This first number has 1, 2, 3, 4, 5, 6 places after the decimal point. This second number has 2. This one has a lot more than 2. And here we have 4. We have to round our answer so it has the lowest number of digits after the decimal point, which happens to be 2. Therefore, my final answer is 24.61. So just like before, I want you to try those 3, pause this video, come back, and see what the correct answers are. And there are your answers for those last 3. H is interesting because your calculator gives you 101.983551. Now, when I round this to have 1 digit after the decimal point, of course, this 8 is going to round that 9 up to a 10, which then gets rid of the 101 and ultimately rounds that up to 102. So this one does appear to be a big round, but because of the way the numbers are, we do have to change that to 102. Let's get back to the notes. We're almost done.
Density, something else I always like to review, because when we get to the gas law unit, we do kind of touch on density a little bit. And this usually students have a very easy time with. It's really not a difficult concept at all. So density determines the mass per unit volume, or how compact the particles in a solid, a liquid, or a gas are. So we just talked about solids, liquids, and gases in terms of states of matter. Solids and liquids are typically very dense relative to their gas counterparts. And that's because gas particles, like we said, are far apart relative to their size. So their mass per unit volume is very, very small. There's not a lot of mass in a given space compared to solids or liquids. So if I take a look at this image, we can assume that both of these take up the same volume. These cubes look like they're about the same size. However, this cube on the left has a lot more stuff crammed into that space. So therefore, we say that the density of this cube on the left is much higher. There is a higher mass per unit volume compared to this cube here on the right. There is not as much stuff crammed into that particular space, and therefore it's not as heavy or it's not as dense, we say. And your equation looks like this. Its density is equal to mass divided by volume. Let's go ahead and do sample problem 3.
Sample problem 3. A sample of aluminum has a mass of 8.4 grams. Let's write that down. The volume is 3.1 centimeter cubed. We want to know what's the density of aluminum. So this one's relatively easy. All you need to know is that density is equal to mass divided by volume. So let's just plug in the mass and the volume. Mass is 8.4 grams. Divide that by the volume, which is 3.1 centimeter cubed. And when you do that, we still have to follow our significant figure rules. Just because we're not doing a significant figure problem doesn't mean we get to forget about significant figures entirely. Sorry, that looks a little sloppy. It's hard for me to look at the number and then write it down on this pad at the same time. So we have to round this number so it follows our significant figure rules. This top number has 2 significant figures, and I'm dividing. Our bottom number also has 2, which means our final answer must also have 2 significant figures. Therefore, your answer is 2.7 grams per centimeter cubed. Units for density are always grams per centimeter cubed because it's the mass per unit volume. So mass is in units of grams and volume is in units of centimeters cubed. If you can use D equals M over V, you can manipulate any density equation. You can manipulate any problem in order to solve for any of those variables.
The last segment of this video is all about the parts of the atom. So let's just go over this quickly. Of course, we have protons, neutrons, and electrons that make up atoms. Your protons have a charge of +1, a relative charge of +1, I should say. And they also have a relative mass of about 1 atomic mass unit. So protons weigh 1 atomic mass unit, which if you remember, back from Chem 1, you did a couple of calculations with those, but you don't need to worry about that now. Protons, of course, are located in the nucleus, and something else you should know is that that's what defines an element. The number of protons is its atomic number. The number of protons in the nucleus tells us what element it is. Neutrons are also in the nucleus, and these have the same relative mass of about 1. So protons and neutrons have about the same mass. And these have a neutral charge. They do not have a charge whatsoever. And your protons and neutrons are kind of crammed together here in this very dense section of the nucleus. Whereas your electrons live in clouds surrounding that outermost part. So your electrons are very, very small relative to the size and mass of protons and neutrons, which is why in this picture they're shown as very, very small. And notice that we have this massive gray cloud that's surrounding this. So these electrons themselves are small, but they're moving around this very large area relative to the rest of the nucleus. And if we were to identify this element, so notice that this particular image has 1, 2 protons in the nucleus. This must mean that this is a helium atom. Again, not that you need to know that, but it's always good to just go back and refresh. And that's where I'm going to stop for this video. Again, just a very basic review of some very early things that you learned back in Chem 1. We're not going to be focusing a lot on this stuff, but it is always good to just review the very basics behind what you're going to be learning next. So if you have any questions, make sure you email me. You stop by and see me at some point. I will answer those for you. Make sure you do that significant figures practice worksheet, and I also submit an answer key to you. So check your work just to make sure you are learning this kind of as we go along and getting a sufficient review of the things that you need to remember. So otherwise, I'm going to log off for now. Be sure to watch the next video all about the mole. So very exciting. So I will see you in that video. Bye.